Right, welcome to the second session then. My name is Heiner Linke. I will be sharing the session, and I'm very happy to introduce Chris Jarzynski from Maryland University on giving a talk on quantum impulse control.
Thank you, and let me thank the organizers for the invitation. Wish I could be there in Santa Barbara. And let me try to share the appropriate screen here. All right, so as the title suggests, I'm going to be talking about how to use impulses to control the evolution of quantum systems. And to set the stage here, let's recall that the quantum adiabatic theorem tells us that if we take some quantum system and start it in, let's say, a given eigenstate of the energy, as illustrated here on the left with a one-dimensional particle in a box in the fourth excited eigenstate. If we then change the system's Hamiltonian very slowly with time, such as compressing the box very slowly, then the system will always remain in that given eigenstate of the instantaneous Hamiltonian. So it'll end up, for instance, in the fourth excited state of the particle in the box. Throughout this talk, when I talk about evolution, quantum evolution, I'm always going to assume unitary evolution, namely the time-dependent Schrödinger equation. So I'm not going to be talking about open quantum systems. And I will also focus specifically on systems with 1 degree of freedom, just for simplicity and because the time is short. But I believe that most of the results, or all of the results that I'll be discussing, generalize fairly naturally to systems with multiple degrees of freedom. As we know, it's useful to formalize this quantum adiabatic theorem by formally representing the Hamiltonian as a function of a product epsilon times time, where epsilon is a smallness parameter, and we set the value of, or we take the limit in which epsilon goes to 0, while holding the duration of the process delta t, while letting the duration of the process delta t scale like 1 over epsilon. In formulating things this way, it's useful to refer to epsilon times t as a kind of slow time, whereas t is the ordinary or lab time. In this talk, I'm actually going to be interested in the opposite limit of fast driving. So here I'm going to have a Hamiltonian, or more generally some perturbation that's acting on the system, where that perturbation scales is a function of t over epsilon. And the duration is going to scale like epsilon. And again, epsilon is a smallness parameter, so I'm going to consider the limit where epsilon goes to 0. So I'm going to consider the limit where the system the perturbation acts very rapidly and over a very short interval of time. And here I'll find it useful to refer to this ratio t over epsilon as fast time. Now, if I apply this perturbation very briefly, only very briefly, then it's not going to have any effect on the system unless it's also very strong. So in order to have some effect on the system, I'm going to insist that the strength of the perturbation somehow become larger and larger as epsilon goes to 0. And it turns out that how we do this scaling has a big impact on the effect that this perturbation has on the wave function. So this sort of perturbation is what I'll call an impulse, and I want to look at how these impulses, what these impulses do to the wave function. So let me start by illustrating the basic idea using a very, very simple, basically trivial example, where I apply a force that depends on time but does not depend on position. So in the quantum context, this just means applying a potential that's linear in the position x. This potential is going to be applied over some interval of time that's centered around t equals 0, just for convenience. And the duration of this interval is epsilon times tau 0, where tau 0 is fixed. And again, tau denotes this fast time. So the perturbation acts over a fixed interval of fast time, which means that as epsilon goes to 0, it acts over an infinitesimal interval in ordinary lab time. Let me assume that the force that's applied in this way has the following scaling. So again, its duration scales like epsilon, but the strength scales like 1 over epsilon. So the force has this scaling. And as we know, if we apply this kind of rapid force to a classical system, this is what's known ordinarily as an impulse. I'll call it a first order impulse. And kind of from introductory mechanics, we know that the net effect of this impulse is to suddenly change the momentum of the system by an amount delta P, which is just the integral under the force. Okay, so again, all of this is very trivial, and it turns out that this extends or generalizes very naturally to the quantum case. If we plug this potential into the Schrodinger equation, take the limit as epsilon goes to 0, we'll see that the final wave function, namely the wave function immediately after the impulse, is the same as the initial wave function, the one immediately before the impulse, multiplied by this phase, e to the I delta px over h bar, where the delta p is the same as in the classical case. This is kind of what you would have expected if you didn't solve the equation, and it's what you get if you actually do solve the equation. So I'll refer to this as kind of painting a phase onto the wave function. Notice that this has no effect at all on the probability distribution associated with this system. It only affects the phase. Okay, so this is the kind of trivial scaling where the strength scales like 1 over epsilon. I'm going to be actually interested in what I think is the more interesting scaling, where the strength of the perturbation scales like 1 over epsilon squared, and I'll refer to this as a second order impulse. So let me assume that this force has the scaling that's shown over here and illustrated over here. The duration scales like epsilon, the strength scales like 1 over epsilon squared, and now I'm going to impose an additional constraint, namely that the integral under this f of t is equal to 0. If that constraint is not satisfied, then this perturbation has a divergent effect on the wave function in the limit as epsilon goes to 0. In the classical case, if we apply an impulse of this sort, then the result that we get, it's not entirely trivial, but maybe not completely unexpected. The result that we get is that there is a sudden displacement in the position of the particle without any change in its momentum. And intuitively, the idea is the following, that initially there's a rapid acceleration in one direction, and then a rapid that's followed by a rapid deceleration. And if the area underneath this curve is equal to 0, then there's no net change in the momentum of the system, just a sudden abrupt change in the position of the system. What's maybe a little bit more surprising is that in the quantum case, we get an exactly analogous effect. If I take this time-dependent wave function, this time-dependent potential with this scaling, plug it into the Schrodinger equation, solve it as in the limit epsilon goes to 0, then I'll find that the final wave function is identical to the initial wave function, just suddenly displaced by an amount delta x, where the delta x is exactly the same as the displacement that you get in the classical case. And this is surely something that has been derived, many times. I wouldn't be surprised to find it as an exercise in a quantum mechanics book, but I haven't seen it anywhere. So if somebody has a reference, I'd be very happy to see that. So what I want to focus on is basically generalizing this result to perturbations that aren't necessarily linear in X. So let me frame, and as I had referred to the first order impulse as painting a phase onto the wave function, here I'm going to say that a second order impulse transports the wave function. In this case, it just translates it by a fixed amount, but I might be interested now in looking at what sort of impulses, what sort of second order impulse might, let's say, stretch the wave function or contract it, or move it and deform it in some nonlinear way. So let me formalize the problem as follows. I have a time-dependent Hamiltonian, which is composed of a kinetic term, some background potential term, which is going to be entirely irrelevant, so you can ignore it, plus this impulse, whose duration scales like epsilon, as before, and whose strength scales like 1 over epsilon squared. And now I can form the problem in one of two ways. I can either say, given the initial wave function just before the impulse and the form of the impulse itself, I would like to solve for the final wave function, the one right after the impulse. Or alternatively, I can kind of flip the problem around and say, given an initial wave function before the impulse, a desired final wave function right after the impulse, I'd like to solve for the perturbation that gives me this time evolution. And in both of these cases, the limit epsilon goes to 0 is understood. So I find it easier to talk about the second case. So I'm going to look at the problem in this way, but one can discuss it in this way as well. Okay, so here it is. Suppose I have a given initial wave function just before the impulse. I want to get a desired final wave function just after the impulse. Here's the recipe for how I design the impulse. And the first step is the following. Let rho, initial and final, denote the initial and final probability distributions corresponding to these wave functions. And now, over the duration of the impulse, I want to construct some rho of x and t, or rho of x and tau that interpolates from this initial distribution to this final distribution. I need to impose some relatively mild conditions that this rho of x and tau is turned on and off gradually at the beginning and at the end of the impulse in this fast time. But otherwise, I'm fairly free to choose this rho of x and t as I wish. Having chosen that, let me define a new function, a cumulative probability distribution, which is just the integral from -infinity up to x of this probability distribution. So, sorry, in the context of this picture, if I look at a particular point x at a particular point time tau, at a particular time tau, C is just the area underneath this probability distribution up that's to the left of x. And as this notation implies, since C is a monotonically increasing function of x, I can invert it and I can ask what's the position such that the probability to be to the left of that position is equal to C at some given time tau. Having constructed this cumulative probability distribution, let me now construct from that distribution this velocity field v of x and tau, which is just the derivative of x with respect to tau at fixed c. And actually, I really should have written this as a partial derivative. We can then use the cyclic identity of partial derivatives to rewrite this as minus the ratio of these two partial derivatives, and that mathematically defines this flow field. And the intuition behind this flow field is fairly easy. This is just the hydrodynamic flow field that describes the evolution of this probability distribution rho of t. In other words, I can rearrange this, rearrange and manipulate this equation to arrive at this equation, which is the usual continuity equation for evolution under this under a flow field v. Okay, so up to this point, I've constructed this interpolation, and in the corresponding hydrodynamic flow field, let me then define a new field, A of x and tau, which is constructed from v by this equation. Just as v is kind of a velocity flow field, this is the acceleration field corresponding to the time dependence of this probability distribution. And now I write down something that looks like Newton's equation. Ma on the left, force on the right, minus the derivative of ui with respect to x. And I claim that this, this equation then defines this time-dependent potential use of I up to some overall function of time, which is irrelevant. And I claim that the potential that's constructed in this way will give us the desired second-order impulse. In other words, if I take this potential, multiply it by 1 over epsilon squared, and apply it to the wave function over the duration of this impulse, then I'll get the desired evolution from the initial wave function to the final wave function. Actually, to be a little bit more precise, I'll get an evolution that takes me from the initial wave function, which has a distribution rho sub I, to some final wave function, which is a distribution rho sub f. I'm not focusing on the moment on getting the phase right over here. Let me just focus on getting the probability distribution right. Okay, so this is the recipe for how to construct this impulse. Let me now briefly sketch the derivation of this result. So again, this is the time-dependent Hamiltonian I'm interested in. In the previous transparency, I defined this field A, and then from that A, I defined the impulse potential using this equation. Let me now define an auxiliary function S in a very similar manner. M times the flow field V is partial of x with S with respect to x. So again, this defines this auxiliary function S up to an overall function of time. And now my claim is, this is straightforward to show, but a little bit involved. My claim is that I can choose that arbitrary function of time so that these two functions defined in this way satisfy the Hamilton-Jacobi equation, which is written down over here. Again, I'm not trying to justify this now, but it can be shown. And now the elements are all in place. Let me make the following ansatz for the wave function. I'm going to say that the wave function can be written down as the square root of some probability distribution rho times this phase e to the I theta, which depends on x and tau, times e to the I s divided by epsilon h bar, where s is this auxiliary function. So this is still a generic representation for a one-dimensional wave function. If I plug this wave function into the Schrodinger equation using this Hamiltonian, take the limit as epsilon goes to 0, then after everything shakes out, I find that I get the following two equations, one equation for rho and another equation for this field theta. Again, I'm not focused at the moment on the phases because I don't have enough time to do that, but you'll notice that this equation for rho is just the continuity equation describing evolution under this flow field V. In other words, what I'm saying is that in the limit where epsilon goes to 0, the wave function evolves under this Hamiltonian in such a way so that its probability distribution satisfies exactly the continuity equation that we want it to satisfy. So the probability distribution gets it from the initial row to the desired final row. And just a quick mention in passing that if the wave function arrives here with some phase that's different from the one we want, we can always use a first order impulse to paint the desired phase onto psi sub f. But again, talking about that in more detail would take too much time. In the final couple minutes that I have, let me briefly sketch a little bit of intuition for why this might work. And this is only partial intuition. Here I've plotted the initial probability distribution rho sub I, the desired final probability distribution rho sub f, and I can imagine these two probability distributions as representing some ensemble of trajectories, ensemble of classical trajectories, where let's say these 3 points over here represent initial conditions for 3 of those trajectories, and these initial conditions are distributed according to rho I of x. If I evolve a trajectory from each one of these initial conditions where the trajectory satisfies this equation over here, then each of these initial conditions will lead to some final condition, which I'll call x sub f, which is a function of x sub I. And by construction, the final trajectories will be distributed according to the desired probability distribution rho sub f. And what this construction shows us is that, again, ignoring the phase, the final wave function and the initial wave function are related by this simple expression. The final wave function at this point x sub f is just the initial wave function at this point x sub I, where these two are related by this time dependence. And then there's this Jacobian factor thrown in to preserve normalization. In other words, if I square both sides of this equation, I get just the usual relationship between the initial probability distribution and the final probability distribution. This equation, in turn, implies that effectively the propagator that's propagating the wave function from just before the impulse to just after the impulse is given by this simple expression over here, which involves a delta function, and that seems to suggest that only a single path contributes to this propagator. Remember that in general, quantum propagators can be expressed as a sum over all possible paths. This expression seems to be saying that only a single path contributes. So how can we get that? Well, if I write down the time-dependent Schrodinger equation over the course of the impulse, if I then multiply both sides of this equation by epsilon squared, rewrite things in terms of the fast time tau rather than the slow time epsilon, I get this equation that's shown at the bottom over here. And now in the limit where epsilon goes to 0, this term in the equation is going to drop out. These two terms, even though they have epsilons, aren't going to drop out because the derivative of psi with respect to tau and with respect to x scales like 1 over epsilon. So these two are order epsilon 0 terms. But the bottom line is, if you ignore this term that's dropped out and you stare at the equation, you realize this is just the time-dependent Schrodinger equation evolving in this potential over here with an effective Planck's constant epsilon times h bar. So the limit, mathematically, the limit of taking epsilon goes to 0 is the same as the limit of taking h bar goes to 0. And in that case, we shouldn't be surprised that instead of getting a sum over all possible trajectories, we only get a sum over a single trajectory, or let's say a discrete number of trajectories. So this is kind of like the semi-classical limit. All right, I see that my time is up. I was going to talk a little bit about what happens when there are nodes in the quantum wave function, where this becomes a little bit more complicated. But let me take you to the summary slide, where basically I've argued that when we apply a first order impulse, the net effect is that it paints a phase on the wave function. This is exactly what one might expect. When we apply a second order impulse, the net effect is that it somehow transports the wave function, and that this transport can be described in terms of a deterministic mapping from initial positions to final positions. So let me leave it with this slide where there's kind of work to be done. This should be extended to multiple degrees of freedom. As I've indicated, this is largely done, although there is still a few details to clean up. It would be nice to be able to extend this to many particle systems, maybe using some sort of mean field approach. And of course, it would be very nice to have some experimental realizations, which might clarify what the difference between a first and second order impulse would be in an experimental setting, rather than in a theoretical setting where we formally are allowed to take limits. And there's this other issue here that involves the nodes of the wave function. So I believe I'm out of time now, and I'll be happy to answer any questions people may have.
All right, thank you very much. And we already have a hand up, Nicole.
Hi, Chris. Thanks for the very nice, clear talk. I was wondering if you know of experimental settings where this technique would be called for. There, say, any particular platforms where some kind of transformation needs to be realized, and it seems like your tool is the tool that fits the bill?
Oh, no, so I don't have any specific applications in mind. I got into this through kind of a related problem of shortcuts to adiabaticity. And there have been experiments where, well, first of all, where these shortcuts have been realized in the lab, and also used as a tool to prepare systems in particular states. So I can imagine that maybe that this could be helpful for preparing a system in a particular state. Like, let's say it's easy to start the system off in the ground state of a particular Hamiltonian, but we don't want it to be in the ground state. We want it to be in some other wave functions. So this might give you a mechanism for boosting it up to that other wave function, but no specific applications where there's this pressing need to have this sort of tool.
Okay, thank you.
Thanks for the question.
Right, the next question is by Emily Townsend.
Hi, I'm not actually Emily. I'm Chris Baldwin.
But there's him.
KITP crowd.
You sort of popped up there suddenly. Okay. Good.
Yeah, so going off of that slide about the semi-classical intuition, is there actually any difference between this problem and if I instead have a classical distribution of particles and just wanted to, come up with a classical potential that would move that distribution around?
No, actually, that's something I didn't mention, but it's kind of amazing that if you formulate the problem entirely classically, so let's say that I have a classical probability distribution, and I want to design an impulse that gets me from some initial distribution to a desired final distribution. The protocol for designing that impulse is going to be exactly the same. So it's exactly the same problem, and that is a little bit surprising because it says that the classical version of this problem fully solves the quantum version of this problem. And I think ultimately the reason why that is that somehow this epsilon going to zero limit is effectively the semi-classical limit.
Right.
And so if we want to see some interesting quantum effect, we don't want it to be an impulse. We want it to be some.
Correct. Yeah, this is, yeah, if you want to look at it that way, yeah, this is saying that in order to design the impulses that we want, we don't need to use anything fancy from quantum mechanics. We can classical mechanics gives us all the tools that we need. Okay, cool. Thank you.
Great. I think next in line was Asa Auerbach.
Yes. If I look at the equations, they look like you have a superfluid and you're giving it a kick and changing its density instantaneously. What are you doing to the currents? You didn't show what the phases are doing, and what condition do you want to put on the currents before and after the kick?
So what happens to the phases is shown. Let's see. Oh, sorry, I went back a little too far. This slide is meant to illustrate what happens to the phase. If my initial wave function is described as a probability distribution associated with a phase at every point in time, and if you'll recall, the final wave function is obtained from the initial wave function by this mapping that takes any initial point to any final point, then under the protocol that's described here, the phase at the initial point is exactly the same as the phase at the final point. So the phase just gets translated, and that's the content of this equation here. And now this little comment that I briefly mentioned down here is the following. Suppose I want some different phase profile for the final wave function. Well, then in order to get that different phase profile, I'd have to go back to one of these first order impulses and just use a potential that's not linear in x, and using a general potential, but with a first order impulse that scales like 1 over epsilon, I can paint an arbitrary phase onto the final wave function. So the bottom line is kind of that the second order impulses manipulate the probability distribution. They move it or deform it, they squeeze it, stretch it, and so forth. First order impulses then on top of that can paint an arbitrary phase.
Okay, but if you physically have an experiment that you want to change the density instantaneously, wouldn't you necessarily cause currents to flow? In other words, that will affect the way the phases are?
Well, the currents are going to flow in this intermediate during the impulse itself. So in an experiment, of course, you're never going to have epsilon exactly at 0. In an experiment, you'll have epsilon take some small value, and hopefully that value is sufficiently small that that the analysis here is a good approximation. It's not going to be perfect. But the point is that in a real experiment, during this finite interval of time, you'll get these large currents that are generated, and those currents are going to be transporting the wave function, transporting the probability distribution associated with that wave function. But if you've designed it right, then at the end, this the acceleration that you get at the beginning is matched by this deceleration that you get at the end, and that's kind of all hidden in the details that I didn't have time to go over.
I see. Okay, thank you.
That also resides in, I mean, the proper way to understand this is through the Hamilton-Jacobi equation, and that really shows how this acceleration and deceleration occur.
I see. Thank you.
Okay, thanks for the question.
Right, I think next in line was Jorge. And we probably just have time for just one or maybe two more questions. No hand from you? No. Then Anatoly.
Sorry. Thank you for the. Oh, sorry. Okay.
Go ahead, Anatoly.
Okay, thank you. Yeah, so I have like one quick comment that maybe not in this context, but in principle, kind of such protocols were sort of discussed in Flock engineering, where epsilon is a period. But also I have like a related question. I think if you go to the rotating frame with respect to your driving term, then you will remove 1 power of epsilon. And then if my thinking is correct, you'll get effective Hamiltonian, which is linear in momentum, like in the leading order of 1 over epsilon. And for those Hamiltonians, actually quantum and classical evolution is the same. I just wonder if you kind of thought about this.
I'm not 100% sure what you mean by that, but I think I know what you're talking about. And if it is, then that's actually kind of the way that I got to this result, by first going to a Hamiltonian that is linear in momentum.
Yes.
And in fact, the thing that's multiplying momentum is just this velocity flow field V of xt.
Okay.
And it needs to be made symmetric, so it's P times V.
Yes, exactly. That's
okay. Yeah, so that's how I got to this. In terms of flow K engineering, my understanding with the flow K engineering is that epsilon is small. In other words, you're driving it very, very fast.
Yes.
But you're not necessarily making it very strong. In other words, the faster you go, you're not driving it more and more strongly.
No, if you want to engineer, you exactly do it. Like, for example, Kapitsa pendulum, because otherwise you will get time Hamiltonian. You always scale amplitude.
Right. Yeah.
This is 1 over epsilon squared. Is more rare, but it was also used, but not in different contexts.
Okay. Right. I'd be interested to follow up on this in the context of flow K engineering, because here I don't have time periodicity specifically in mind.
Okay. Thank you.
All right, we are kind of out of time, but Jorge, if you're quick, you can have another shot at it.
Does a magnetic field make anything interesting? A peak?
Probably. I actually haven't looked at this at all with magnetic fields. I'm afraid of magnetic fields. Sorry.
All right, let's leave it at that. Thanks. Thanks very much, Chris.
Thank you.